Yo, what up, physics people? We're starting a new chapter, chapter 20. Gonna talk a lot about electricity, electrodynamics in this chapter. All right, so okay, kind of a lot to cover in this one, so bear with me. We're gonna try to get through this as efficiently as possible and get you through this. And today we're gonna talk about current, voltage, and resistance. Current, voltage, and resistance, and it's in regards to electrodynamics. Cool? Section 20A, let's go ahead and do it. So the last two chapters dealt with stationary charged objects, also called electrostatics. However, charges do move when they are attracted or repelled by other charges. They may set up a current, which is defined as a continuous flow of charge. Cool? The study of the causes and effects of current electricity is called electrodynamics. All right, and the motion of electronics creates a current in metal. So usually when we think of the word current, we will probably think about like a river's current. A river has a current that flows from upstream to downstream, or from, maybe to simplify it, from the mountains down to the ocean. All right, there is a direction of flow. We could think of electrons or positive and negative charges flowing in very similar ways. So that's why we call it current. Electrical conduction in metals begins with a potential difference in the metal. So go ahead and write this down. I'm going to walk you through kind of basically like a really simplified way on how this works. All right, so we're going to use pictures. Ready? Okay, let's say that we have a wire here, and inside the wire there are positive charges and then there's a negative charge. All right, and over here on this side we have a positively charged rod. All right, just kind of just chilling here, not close enough that it's going to affect the wire at all. All right, but if we bring this rod closer to the wire, what's going to happen, or what should happen? What would you expect to happen? Because all of these are positive charges, you would expect this negative charge, this low negative charge, to move towards a positive charge. So it decides that it wants to be closer because opposite charges are attracted to each other, and these two guys switch, and now this negative charge is one step closer to the positive charge. All right, but it's not good enough. All right, they will continue to move. All right, the negative charge is going to switch with the next positive charge and get closer, and eventually it's going to be attracted to this negative charge. This negative charge is going to be attracted to the positive rod. Now, this wire extending further this way is going to have more negative charges in the wire. So what's going to happen? These negative charges are going to flow. And this is the basic idea behind electrical conduction. All right, where we have negative charges are attracted towards the positive sides of things. Now, when we have solid conductors, like metals, electrons are usually carrying the current. But if we have solutions, aqueous or liquid solutions, we have things that are called electrolytes inside of these solutions. Electrolytes are materials that are able to conduct electricity when they are dissolved. They separate into positive ions or cations. All right, so the positive ions are called cations, or negative ions, which are called anions. All right, so there you go. Good for us, we define those things. Since current is a flow of charge, it is natural to define a unit of current known as the ampere. So, or we call it amps for short. So 1 ampere is defined as 1 coulomb of charge per 1 second. Okay. Now you might be wondering, well, which direction does it flow? You're probably not wondering. You're probably just copying down notes and not really thinking too much of this stuff. Well, the truth is, the choice is arbitrary, and I guess maybe a better way is perspective. It's a matter of perspective. How do you view this flow of charge? Well, If you're paying attention to the negative charges, you would say that it is flowing from to the positive side, right? Because we just saw the journey of the negative charge move down the line, kind of going closer to the positive charge. If you're paying attention to the negative, it's flowing this way. But you could also pay attention to the positive charges, and they tend to flow to the opposite side. Okay, so when it comes to current direction, it's really up to you on how you want to view it. Now, the textbook convention says that, and again, this is how this book is choosing to present the information. The current flows from a higher potential or positive charge to a lower potential negative charge, which is the opposite of electron flow. Now, potential difference is a difference in electrical potential between two positions. And well, the way the book's going to explain it is like point A to point B from two different spots is going to be the amount of voltage between two different spots. All right. Potential difference can be positive, negative, or zero, and we use polarity markings in order to signify these. Positive, or the plus sign, for higher potential, and negative sign for lower potential. Differences in electrical potential can be produced in several ways, but we are going to measure them in units called volts. Now, a volt is defined as 1 joule of energy per every 1 coulomb of charge. And this is kind of a recap of something that we talked about before. Just kind of keep this in mind. Now, we're going to go ahead and look a little further into what this coulomb is. 1 coulomb is defined as the total charge of a specific number of fundamental charges. Now, when we say fundamental charges, what we're looking at is the absolute value of the charge of an electron. So 1 coulomb is equal to 6.24 times 10 to the 18th electrons. All right? Or it's defined as 1 ampere per second, or ampere seconds. Cool, got that down. Now we're going to go ahead and talk about the voltaic cell. Kind of interesting, and kind of where probably gives us a better understanding of where the modern battery comes from. All right, probably the most convenient source of steady potential difference for laboratory use is one based on the voltaic cell. So there was this dude, Luigi Galvani. Basically, what they figured out is that you can convert chemical energy to electrical energy. And this was first observed by Luigi Galvani as he was studying the anatomy of a frog. So basically, he had this frog sitting on this metal tray, and then when he went to touch the frog with his scalpel, the frog leg moved. And he was freaked out. You'd probably been extra freaked out. But when he touched it with his scalpel, the touch established an electric current which contracted the frog's leg muscles. And Galvani touched the nerve with different metals and discovered that some metals cause a stronger contraction than others. He thought that the frog's tissues were the source of the current, but after viewing Galvani's observation, Alessandro Volta correctly concluded that the source of the current is the contact of the two different metals being the tray and the scalpel. All right, so what we have here is an understanding of if you have two different metals and you have a conductor between them, all right, you can actually you conduct an electric current through those two different metals and through the conductor. All right, and this is actually where we got our idea of the first battery. Now, electrodes are the metal conductors in the voltaic cell. A cathode has a stronger attraction for the electrons, and the anode is the exact opposite. That is another electrode, but it is the one that has less strong attraction for the electron. So when we talked about Luigi Galvani kind of conducting it, and he figuring out that different metals have different effects, he figured out that one is what we call a cathode and the other is called the anode. The electrons flow from the anode to the cathode, and conventional current is directed from cathode to anode, and the circuit is formed if the path is closed. So it's really important to understand that the circuit is formed if the path is closed. As this circuit going from from anode to cathode is going back and forth, it actually helps conduct that current through. Now let's go ahead and talk about primary cells. Primary cells simply convert chemical energy to electrical energy, and these are one-way reactions. So it cannot be recharged. The standard battery cell that you use in a flashlight are that you would use in like a flashlight are considered to be primary cells. Unlike primary cells, storage cells rely on reversible or two-way chemical reactions. Therefore, storage cells can be recharged by the addition of electrical energy, which is converted back to chemical energy. Probably the most familiar storage cell is found in a car battery. All right, so car batteries are the most familiar storage cells. These batteries usually consist of a group of connected storage cells. Technically, a battery is a series of cells. Rechargeable storage cells that use lithium-ion and nickel metal hydride technology are found in batteries using like cell phones, digital cameras, and laptop computers. So anything that's rechargeable falls under this category. Another term that you might hear applied to voltaic cells is a dry cell. A dry cell is a primary or storage cell that has an electrolytic paste instead of a liquid solution. The car battery has a liquid solution on the inside, and batteries like D batteries, like D cells, these are considered dry cells. And they're usually easier and safer to use than wet cells because they have a paste inside of it instead of a liquid. Now let's go ahead and talk about resistance. Every material tends to impede the flow of charge. In wires, the free electrons collide with electric fields of the inner atoms, and such collisions convert the kinetic energy of free electrons to kinetic energy of the inner atoms, and then also temperature also affects the flow of charge. So there is resistance for flow of charge. Now resistivity, represented by the Greek letter rho, R-H-O. Let's go ahead and so it's not letter P. This is rho. All right, is the tendency to impede current. The tendency to impede current. Good conductors tend to have lower resistivities, especially compared to poor conductors. Only superconductors, certain materials at low temperatures, which are less than 138 Kelvin, have zero resistivity. All right, so we're going to start talking about resistance. Now, a resistor is any circuit component designed to convert electrical potential energy to thermal energy, and in turn, it produces a potential difference in the process. Okay, so you guys might have heard about this, especially if you guys have ever done any work with electronics. They often have resistors in them, but this is any circuit component designed to convert the potential energy to thermal energy. And long, thin wires with higher resistivity values make better resistors than short, heavy wires with low rho values. So if you ever want a good resistor, you would typically want one that has long, thin wires. Now resistance, different than resistivity, is equal to the resistivity times the length of the object's current path divided by the cross-sectional area. If you ever had to figure, we can give you these values are found on a table on page 451 in your book. Resistance is measured in the unit of ohms, and this is Ohm's law in order to figure this out. So An ohm is defined as 1 volt for every 1 ampere. So going back one slide just for a second, this was Ohm's law, V is equal to IR, where if you ever want to find the potential difference or the voltage, it is equal to the current times the resistance. Okay, and then going back even further, if you ever had to find the resistance is equal to this guy. All right, so a math problem could be asked like this one, where we're just using basic multiplication and division to either solve for the voltage, the current, or the resistance. Okay. The last thing we should talk about is power. Now, power is expressed in joules per second, or also called watts. Okay, so 1 kilowatt is equal to 1,000 watts. That should make sense based off of a whole year's worth of using metric units. A kilowatt hour is a unit of energy. So 1 kilowatt hour is equal to 1,000 watts times 3,600 seconds, because there are 3,600 seconds in an hour. So you can say that 1 kilowatt hour is equal to 3,600,000 joules. Okay, and last slide, last thing you have to write down, and these are the formulas for electrical power. Make sure you guys keep your formula page up to date in your notebooks. All right, so power is equal to the voltage times the current, or you can say it is the same thing as the current squared times the resistance, all right, also known as Joule's law. Or you can say that power is equal to the voltage squared divided by the resistance. All right, that's it for this lesson. I hope you had a good time writing down these notes. I guess that's it. See you later. Bye. Peace.